All right, good afternoon, class. This is lesson 16, section 4.3, as we continue in chapter 4. So far in chapter 4, we've been discussing vector spaces, subspaces of vector spaces, and then we've also gotten into some special cases of types of subspaces as they relate to the matrix. 3, we really want to start to delve into more properties about our vector space that are kind of unique to it, so that it's not just like some arbitrary set of vectors or something more special about a vector space. In particular, what we have from 4.3 is that every vector space has a basis. Every subspace has a basis. So what is a basis? That's really what we want to focus on in today's section of for lesson 16. Okay, so let's take a look. What is a basis? We're going to start with a definition and then look at some examples. So, hold on. I appear to be missing one of my markers. I found it. Okay, we're good. So, what is a basis? Well, first of all, start with the definition. Let H be a subspace of a vector space V, right? Okay, so far, nothing new. We've done this before. Now we're going to consider a set of vectors, and we're going to use this fancy script B. Kind of looks like a cursive capital B. This is going to be the notation we're going to use for a basis. So note this capital B, it's not like a standard capital B, which could be a matrix, right, in this class. This script B is a set of vectors, all right? Then this script B is a set of vectors of V such that B is a basis for H. So a basis is a set of vectors for some space if the following happens. Number one, B is linearly independent. In other words, the vectors in this set, they need to be linearly independent of each other. If you take the vectors in the set B and you put them together in a matrix, well, when you row reduce it, you should have a pivot in every column. They must be linearly independent. And two, to be a basis means H equals this span of these vectors. In other words, a basis is the set of vectors which makes up the building blocks for some space. So in fact, we've already actually seen examples of a basis in some of the previous examples going all the way back to chapter 1. We just didn't call it a basis yet. For example, consider like the vector space V equals R2. Right? We're very familiar with this vector space. We kind of keep seeing it over and over and over again. Well, let B equal the set 1, 0, 0, 1. First of all, this set is linearly independent. Why? Well, if you put them together into a matrix, we see there's a pivot in every column. This is linearly independent. Okay, check. But then what else is true? We already know from what we've discussed in this class that R2 is the span of 1, 0, 0, 1, right? In other words, R2 is a set of all possible vectors which could travel in the x-axis direction or could travel in the y-axis direction or any combination of them, right? every vector in R2 is a combination of these two vectors, which we've discussed before in previous sections. So what's new here, the new piece is that we're highlighting the set of these vectors are actually more special. These are, in fact, basis vectors because, one, they're linearly independent, and two, these are the vectors which make up the building blocks for this space. Now, there is a point I want to highlight here in that a basis does not always have to be only one thing. For example, in R2, we could think about a different basis. So I'm going to say B subscript 2. We're talking about a different basis here. Let's say this is the set of vectors 1, 0, and 1, 2. Okay, well, this is a different set of vectors from the basis that I first described down here. But these are also linearly independent, right? If you put them together in a matrix, we see we have a pivot in every column. So it's linearly independent. But it's also still true that R2 is the span of these two vectors. Why? Well, R2 is a two-dimensional space. So all you need to span R2 is two unique directions, two unique axes to move in, and that's enough to give you the ability to move everywhere in the space, right? Now, in this case, you can imagine instead of an x-axis and a y-axis, you would have this x-axis, right? But instead of moving in the, instead of having a y-axis, you would have instead some other axis here that you could move in, right? This would be the axis that follows the vector 1, 2. So this one's kind of funny, but they are going in unique directions. These are vectors that are going in linearly independent directions. These two vectors are linearly independent, and I have two of them. R2 is a two-dimensional space, so I need two unique directions to travel in, and this also spans R2, right? You can imagine, well, no matter what vector I'm imagining, vector x, y, well, all I got to do is, move along the x-axis direction, and then I would have to move in, I'll call this y, just because we're used to having the other axis called y, but obviously this isn't a vertical axis. This axis is kind of at a slant. But even though it's at a slant, I can travel along this x-axis, and then I can travel in the direction of this new y-axis, and I can still get to whatever point I like. So this is, in fact, a basis for R2, and these are two different bases for R2. So there's no limitation in terms of what you're allowed to use to make your basis, so long as they are linearly independent and you have enough of them to span your space, then you're good, right? So in fact, there are infinitely many bases for R2. Because you can imagine I could change this 1, 2 to be 1, 3, 1, 4, 1, 5, 1, 6. They're still linearly independent. I would still have two unique directions, and that's all I need to be able to travel everywhere in R2. In terms of practical application, you can imagine, you actually might recall from maybe some high school classes or middle school classes where there were sometimes those robotic clubs where the whole job was that you were given a robot on some kind of table, and you wanted to program the robot to move around on the table to get around obstacles, right? Well, in that case, you would need your robot to be able to, move forward or move backward. It would have to have one axis of direction it could move in, and it would also need some other direction. It'd have to be able to move in two axes, in order to traverse the entire table. Well, so long as you have two unique directions you can travel in, that's a perfectly valid way to traverse some kind of space. So in terms of applications, depending on what you're working with, you might want a different basis to handle different situations. In fact, you can imagine you could also design a basis for the movement of a lunar module, right? You want some lunar module or a Mars rover or something. You want it to be able to move around in different directions, but you want it to be able to traverse in any possible direction. Well, then you need to give it the ability to travel in unique directions, to travel along unique axes. They don't necessarily have to be the X and Y axis, but they have to be unique directions. So this is a basis, and this is a basis. Okay, good. So we have these examples in two-dimensional space in R2. What about in R3? What are other kinds of questions you could be asked in this sort of section? Well, we could see a situation of, let's say, so here's another example. Let's say I give you three vectors. V1 equals 0 to -1. V2 equals 2 to 0. And let's say V3 equals 2, 4, -1. Right? I give you these three different vectors, and let's say that H equals the span of these three vectors. Okay. Now, is this a basis for H, right? If I let B be the set of V1, V2, V3, is this a basis? Well, first of all, we already have by assumption. We're told in this problem to let H equal the span of them, the span of these vectors. But the next question we have to answer, because there are two pieces to be a basis, we need to next answer, are these vectors linearly independent? Because if they are not linearly independent, this is not a basis. Okay, so how do we check? Well, we need to see if these vectors are linearly independent. How do we do that? We could put them together in a matrix, row reduce them, and see, do I get a pivot in every column? However, you might notice just by looking at these, note V3 equals V1 plus V2. In other words, this third direction, V3, is a linear combination of V1 and V2. Well, if that's the case, is V3 linearly independent? No, it's not an independent direction because it's a combination of V1 and V2. So this is not linearly independent. Not linearly independent, so not a basis. But remember what we talked about from 4.2. If you have the span of some vectors, we only need the linearly independent vectors, right? We don't need V3 because V3 is already a combination of V1 and V2. Which means if H is the set of all combinations of V1, V2, V3, well, V3 is already a combination of V1 and V2, which means I could just rewrite this as a span of V1 and V2, right? I can drop V3 because it's dependent. It's not an independent direction. Well, now with that in mind, what can we then create? If I instead modify B to be the set V1 and V2, so I just threw out V3. I threw out v3 because it's dependent. It's a combination of v1, v2, so I really don't need it. It's already included in here. And now what happens? Well, now we can see v1 and v2. They're not multiples of each other. So now this is linearly independent. And we already have h equals this by the initial assumption we're given. So now this b is a basis for h. Okay, so what are some things we can say about this? Well, first of all, these vectors v1 and v2, these vectors are inside of R3. So the possible combinations you can get from v1 and v2 are also in R3. H is a subspace of R3. Well, remember from last section, just because you're inside of a space does not mean that is the dimension of your subspace. The dimension of your subspace is the number of independent directions you can move in. So H is a two-dimensional subspace of R3. Also note H does not equal R2. Again, the dimension of your space, that does not tell you your R2 or R1 or anything like that, because H is still inside of R3. The vectors that are in this set of H, in this subspace of H, these vectors have 3 entries. These vectors only exist inside of R3. So this is a subset of R3. This does not equal R2. Right? So I want to really clarify this and emphasize this. Okay. What else can we say? Well, we can also highlight, what does this actually mean, like visually? Well, a two-dimensional space, that's a plane. Like the XY plane, you have 2 axes, 2 directions you can move in. A two-dimensional space is a plane. So what is this H? Well, it's a plane where it's the plane that is precisely any combination of v1 and v2, right? That's what this plane is. It just so happens v3 was already on that plane because v3 was a combination of v1 and v2, right? You can imagine if I hold these markers, and this is v1 and v2, right? I can move in this blue direction. I can move in this red direction, right? And these are 2 unique directions. This is v1 and v2. It turned out that v3 was a combination of v1 and v2. Well, the fact that it's a combination of v1 and v2 means it's inside the same plane, right? It's inside the same plane. It's not really giving me a unique direction to travel in, right? Because this now black marker I'm holding, that's really just a combination of this blue and red direction. So this isn't a new direction, right? It's not increasing the dimensionality of this. So if I remove the black marker, it's still the same thing because I can still travel anywhere that's a combination of these 2 directions. To make it truly 3-dimensional, I would need a 3rd direction where now the black marker, 3rd direction that is unique of these 2 directions. But v3 does not go in a unique direction, so we don't need it. We only need the 2. All right. Maybe that made sense, maybe not. But if you have questions, by all means, do let me know. All right, great. So we have this example, but what am I getting at? Well, we have this notion that we've just demonstrated here that sometimes if you start with something which is the span of some vectors, you can drop the dependent ones and it doesn't hurt anything. It doesn't change anything. This phenomenon we're demonstrating here is actually something called the spanning set theorem. So let's write it out. The spanning set theorem. What is the point of this theorem? Well, the point of this theorem is going to state that we can do exactly what we just did in this example. That if you have a set, or if you're spanning a set of vectors, but some of them are not linearly independent, well, the linearly dependent ones you can just drop and it doesn't change the span. So here's our theorem. This is called the spanning set theorem. All right, and I don't know why my blue marker is dying. This was brand new, but I guess I'll have to get another one. All right, no matter. The spanning set theorem, what does this say? Well, let S be a set of vectors. Doesn't matter how many. Let's just say that there are P vectors, V1, V2, ... up to VP. There are P of these vectors. And let's say let S be a set of vectors in V, okay, where V is our vector space. Great. Now, let H equal the span of these vectors. So this is just like the example we were just talking about. You have some space, which is the span of some vectors, but maybe it turns out one of the vectors is a combination of the others, like we saw where V3 was V1 plus V2. Maybe there's some vector which is linearly dependent on the other vectors. So if one of the vectors, one of the vectors in S, let's just call it VK. It's just, the K is arbitrary, right? VK is just one of the vectors that's inside of S. We're just saying, let's suppose one of them is a linear combination of the other vectors. All right, in S. Yeah, let's be clear with the notation. In S. Then, if I let, now this is a new set. I started with the set S. Now I'm going to create a new set B, which is the set, let's say B equals the set S, but I'm going to remove that problem point. I'm going to remove the point which was linearly dependent. So when I remove that point, then this new set, B, still spans, this B still spans H, right? Which, as we've discussed, if you have a vector which is linearly dependent, well, it really just turns out that it's a combination of the others. And if it's a combination of the others, it's included in the span of the other vectors. So dropping it really doesn't lose anything because that dependent vector is really already a combination of the others, right? So in this fashion, you can continue dropping the linearly dependent vectors until the set B becomes linearly independent. Then B is a basis for H. So you can imagine this as a sort of recursive algorithm, right? For any of you computer science folks, if you imagine this as a recursive algorithm, you start with a set S of P vectors, and you have that H is the span of those vectors. Okay, so you go through your vectors, you check, are any of them linearly dependent? If they are, you drop the dependent vector, and then you check again. Are the vectors linearly independent? If you find which is dependent, you cut that one out. You keep going and recursively repeat, and you keep creating a new set B each time you keep removing a vector until you've removed all of the dependent vectors and there are only independent ones left. Once that happens, then your set that remains, all of those vectors are linearly independent, which is a requirement to be a basis. And then H already equals the span of it because you can drop the dependent ones. Therefore, you can then create a basis from any set like this. Right? So that's really where the power comes from for this. And in fact, we can use this theorem to create a basis for the column space, the null space, the row space, all of those other subspaces that we discussed in 4.2. So now let's see an example of that, applying what we've learned here in 4.3 to those other subspaces that we discussed in 4.2. All right, well, how does this work? Well, first, we need a matrix A in order to talk about column space, null space, and row space. So here's our matrix A. And in fact, you can see some example problems like this, which are in the homework. So understanding what I'm about to do is going to tell you how to do that homework problem for homework 4. All right, so we want to find the basis for the column space of A, the null space of A, and the row space of A. This is what we want to try to do. All right, let's suppose my matrix A is, let's make it interesting. Let's say the matrix A is a 4 by 5. All right, I have 1, 4, 0, 2, -1, 3, 12, 1, 5, 5, 2, 8, 1, 3, 2, and lastly, 5, 20, 2, 8, 8. Okay, so we have this matrix. And I'm also going ahead and save us the trouble of, I'm going to go ahead and tell you what the reduced echelon form of this matrix is. The reduced echelon form of this matrix is 1, 4, 0, 2, 0, 0, 0, 1, -1, 0, and then 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. All right, so we can then highlight our pivots. Also note, this is the matrix A. This is like the coefficient matrix for a matrix equation. This is not an augmented matrix, right? So this last column is not an equals column, which means it's perfectly fine to have a pivot in the last column. That doesn't mean anything for this matrix. Having a pivot in the last column is only a problem for augmented matrices. This matrix is not augmented, so we're good. Okay, so how do we go about solving this? Well, first, just for sake of ease, and so I have enough space here, I can label each of these columns as A1, A2, A3, A4, and A5, right? And we already know from section 4.2, what is the column space? The column space equals the span of all of the columns. Okay, so now what can we do with this? Well, based on the spanning set theorem, I don't need all of these columns. I only need the linearly independent columns, which means for any columns which are actually linearly dependent, I can throw them out and it doesn't change anything. Okay, well, which ones can I throw out? I can throw out the columns which did not have a pivot. Well, column 2 does not have a pivot, and column 3 did not have a pivot. So I can throw them out. And now, what's my column space? My column space is the span of A1, A3, and A5, and these are also linearly independent. So I can find a basis for my column space. So I can do basis, and we can do like subscript C, C for column, right? So this is basis, subscript C. This is the basis for the column space. And this is a set of the independent columns. 1, 3, 2, 5. 0, 1, 1, 2, and -1, 5, 2, 8. All right, and so we found our answer, at least for the column space. Now, a couple things I want to highlight here. One, the column space is the span of a set of vectors, right? And remember, span is a set of all possible linear combinations, which means this column space is an infinite set. It's a spanning set. This is an infinite thing. The column space is the span of something. If all you write is the column space equals set A1, A3, A5, that is wrong, right? The column space is the span. Having this word here is super key and super important. If you drop span here, your answer is wrong and you will lose points, right? Because we want to be specific with the vocabulary we're using here. The vocabulary matters. Whereas the basis, there's no span here. The basis is a finite set. The basis only contains these 3 vectors. It contains nothing else. It doesn't contain any combination of these vectors. It doesn't contain any multiples of these vectors. A basis only contains a finite number of vectors. In fact, this is always going to be the case for any finite dimensional space. It can get a little bit funny if you're dealing with some kind of theoretical infinite dimensional space. But again, I've kind of hinted at that before in previous sections. That's kind of beyond the scope of this class. We're not going to talk about that in this class. But if you took a more advanced linear algebra class or other more advanced math classes, or possibly maybe some physics classes, you might look at infinite dimensional vector spaces. Then things can get a little weird and fuzzy. But for the sake of this class, the basis is always going to be finite, right? There's nothing else in here. There's no span. The span is the entire space. The basis is the set of vectors that you put in the span. All right, so I want to really emphasize that here. So we found the basis for the column space. What about the null space? Okay, well, the null space is a little bit trickier. Remember that the whole point of the null space is to find the set of X such that it's a solution to the homogeneous system, right? Remember, the null of A is a set. It's an infinite set of all the X, well, possibly infinite. It might be finite, but it's a set of the vector X's mapped to 0. Well, that means for solving this question, now I want to think about, well, what happens when I augment with 0? Right? Because now I'm trying to find the solution set. Okay. Well, now the funny thing here is in the lecture notes, I use the letters A, B, C, D, E for the variables. But we can also recall that this is, each column corresponds with a variable. We can call them x1, x2, x3, x4, and x5. So this labeling that I'm doing in this video on this board is a little bit different from what's in the lecture notes, but you're going to get the same final answer. All right. So what am I getting at? Well, we can see right away x2 and x4 are free because there's no pivots in those columns. They are free variables. Okay, so only x2 and x4 should appear in the parametric vector form, right? Remember that from past sections? Okay, so now what's the rest? How about x5? x5 equals 0. We get that from the third row. Okay, great. What about the second row? This says x3 equals x4 if I add this over. Okay, that's nice. What about x2? Well, x2 is free, x4 is free. What about x1? x1 equals -4 x2 minus 2 x4. Again, if I subtract these two pieces over to the other side. All right, great. So we have all our pieces. I can now construct what x looks like. X is a vector with 5 entries because there are 5 rows for A, or sorry, 5 columns. What's x1? Well, it's this equation. -4 x2 minus 2 x4. What's x2? Well, it's free. Okay, what's x3? It's x4. What's x4? Well, it's free. And then lastly, x5 equals 0. So notice, before I pull it apart in parametric vector form, at this step, the only variables which appear in this column vector are my free variables. That's how you know you've done this correctly. If you have variables appearing in this vector which are not free, that means you've done something wrong. You need to finish solving for the variables. Okay? So we can pull this apart. We have x2 times -4, 1, 0, 0, 0, plus x3 times -2, 0, 1, 1, 0. In other words, what is my null space? It's any x vector, which is any combination of these two vectors. In other words, my null space is the span of these two vectors. Okay, and then what is my basis? Well, then my basis for the null space, again, it's a finite set. It's not the span. The null space is the span of something. The column space is the span of something. Subspaces, vector spaces, these are generally infinite sets. They are the span of something. But a basis is a finite set. So my basis for the null space, well, I'm running out of space, but it is the set of these two vectors, right? It's a finite set of those two vectors. So we found a basis for the null space, basis for the column space. Lastly, what about the row space? Now here we have to be careful. What to be careful? Well, for the column space, I could just take the columns from the original matrix A, and that was fine. Well, for the null space, or sorry, for the row space, it only works so well. Why is that? Well, let's check. The row space of A, we know by definition, it is the span of, for the sake of space, I'm going to label these rows as row 1, row 2, row 3, row 4. We know it's the span of these rows, right? Okay, well, that's all fine and good. But just like column space, just like null space, we only need the linearly independent rows. How do I know which rows are independent? Well, that comes by looking for the pivots. Now, here's where the trickiness comes in. This is the row-reduced echelon form of the matrix, right? The issue here is that When you row reduce a matrix, remember how sometimes you would swap rows during that row reduction process? For this problem, I've only told you what the reduced form of the matrix is. I didn't tell you the steps to get there. So for all we know, what if it just so happened, right? It would one, row 2, row 3. But what if during the row reduction process, row 3 and row 4 swapped with each other? Well, then in that case, I don't want row 3. I want row 4, since row 4 has the pivot. So what are we supposed to do? How are we supposed to know which rows to take? Well, lucky for us, row reduction does preserve the directionality of these row vectors. So in other words, instead of taking the original rows, we can just take the rows from the reduced form. Now, we can't do this for the column space, right? So there is a warning here. So for a row vector, I'm just going to write it as a row. 1, 4, 0, 2, 0, 0, 0, 1, -1, 0, and lastly 0, 0, 0, 0, 1. Right? My row space is the span of the reduced rows because the row reduction preserves the row vectors. Now, when you reduce columns, it modifies the columns. It's no longer the same column. It's no longer going in the same direction. So for the column space, you cannot just take and pick the columns from the reduced form, but for the row space, you can take the rows from the reduced form, right? So we have this span, and in fact, what is the basis? Well, my basis for the row space is just the set of these 3 vectors. Again, the basis is a finite set. The row space is an infinite set. It's the span of something. The difference in the notation here is super key, right? You don't want to flip around the span here. Okay. So that's going to show us how to get the basis for the column space, null space, and row space for any matrix A. All right. Now, before I close up, let's go ahead and look at today's participation question. This is participation day, what is it, 15? Yeah. So I'll go ahead and share my screen. Here we go. Okay. So we can see here, all right, here's some vectors. Let B be a set of vectors. Does B form a basis for R2? Okay. Well, first of all, to be independent. However, these vectors are in R2, but I have 3 of them. Is it possible to have 3 linearly independent vectors? Well, no. Why? If I put these vectors together into a matrix and try to row reduce them, because I only have 2 rows, at most, I can only get 2 pivots. But if I can only have 2 pivots, that means one of these vectors is linearly dependent. If these vectors are not linearly independent, then it is not a basis. So to answer today's question, does B form a basis? The answer is no. And so quite literally, that's all you need to type. You can just type no, and that'll get full credit. The whole point to highlight here is that this is not a basis because there's too many vectors. Because R2 is 2-dimensional, that means every basis for R2 will only have 2 vectors. So because there are 3, there's too many. It's impossible to get a pivot in every column. Therefore, they're linearly dependent, and this is not a basis. Okay? All right. So that's all for today. If you have other questions, please, by all means, do email me. We can talk about it. Otherwise, office hours will be next week on Tuesday and Thursday. Best of luck, and I will see you next time.